So now that we have looked at the plane wave solutions both in a lossless dielectric as well as slightly conducting media, I believe we are ready to handle boundaries. Okay, so just like in transmission lines, once we studied how voltages and currents can be pictured as movement of waves, we next looked at how to terminate these transmission lines at the loads and what are the consequences thereof, right? And we evaluated things like reflection and transmission coefficients. So we are going to do something similar going forward with the three-dimensional electromagnetic fields. But before we dive into taking up a plane wave intersecting at a dielectric boundary or a dielectric conductor boundary, we need to know what exactly happens at the boundary. Okay. So, in the case of our transmission lines, we did have these boundary conditions. We did not quite call out these boundary conditions explicitly. Right. So, point A is the end of the transmission line where I am connecting my load, right, and the boundary condition that we chose here was quite simple, right, which was the voltage, I am going to call it A minus. A minus is just a very infinitesimal point to the left of A, right, is the same as the voltage A plus, V at A plus, right, a small distance to the right of A, right. So, since they are electrically shorted, we do not expect the voltage to change, right. So, V A minus we said was simply the sum of onward and return waves, right, and on the right hand side V A plus was simply the voltage drop across the load. Similarly, we also said that I at A minus was I at A plus, right. So, whatever currents are flowing in the transmission lines to the left of A, the same currents would have to leave A, right, in the right towards the load. So, while these were not explicitly called out as boundary conditions, it is very simplistic, right. We are just equating the voltages and currents on either side. The currents are equated because if they were not equal, we would expect to see buildup of charge at A, right, which would increase the voltage at A. And this, if it were to happen in a continuous fashion, would essentially lead to infinite potentials, right. So, essentially the continuity of charges, right, or local conservation of charges gave us these so called current and voltage boundary conditions, right. So, in the case of electromagnetic fields in dielectric media, we are going to come up with generalized conditions for the electric and magnetic fields, right. And this of course is applicable in any situation you may think of, right. So, it is more general than the voltages and currents we looked at in transmission lines. Okay. So, before we dive in to that straight away, there are two concepts that we will introduce. Although mainly theoretical, it is a very useful tool in order to at least study some simple geometries, right, and simple cases, and that is the concept of surface charges and surface current. So, remember, in a purely dielectric media, we don't have any free charges, right, or mobile ions. So there are no charges or currents, right. But now that we allow for a certain amount of conductivity, a non-zero amount of conductivity in certain media, we can certainly see the presence of charges or flow of current, right, in these media. So the surface charges is a concept that is not perhaps very new. Right. So assume this volume has a charge density rho, which is in coulombs per meter cube, right. Right. And what I do with the thickness of this volume that I am considering, right, is I am going to slowly shrink that, right, to an infinitesimally small value, right, and in the limit, right, the charge that is on a sheet, right, that is what I call the charge density, right. So I call the charge surface charge density rho s is essentially in the limit d goes to 0 rho times d, right. So of course as d closely tends to 0, rho has to go to infinite in order to have a finite value for rho s, right. Even in the conductors that we see around us, we talked about something called the skin depth, right. So these can be extremely thin values, right. So in the case of a perfectly electrical conductor, I can hope to have charges reside just on the surface, right. So remember that this concept is the same as the sheet charge density. That we saw on capacitor plates, right. So in our ideal capacitor model, we assumed two plates, right, one with a positive charge and one with a negative charge, right. And there also we came up with a surface charge density, we called it sigma there, right. And it's the same concept here, right. So I have basically charges residing just at the interface of the surface, right, of the conductor. So this is a important concept. We will be using this, right. Now that we are talking about boundaries, the question is, can there be charges or currents at the boundaries, right. So remember the units for rho s is coulombs per meter square, right. So we have rho, which is charge density, is coulombs per meter cube, multiplied by d, which is in meters, gives us coulombs per meter square. So the same situation for current, right. So if I have a certain volume current density J that's flowing through this volume, and if I were to just shrink the thickness, right, over which this current is flowing, I end up with a surface current Js right. So, I am scaling the vector j by the quantity d, which is vanishingly small, right, and I end up having these currents confined to just the interface of the surface, right. So, remember the units of Js is ampere per meter. Remember the current density was amperes per meter square, right, and so the units for surface current density, right, is amperes per meter. All right. So, let us consider in general an interface between two media, right, with parameters, right, epsilon 1, mu 1, sigma 1 and epsilon 2, mu 2 and sigma 2, right. We will call this medium 1, medium 2, and as a boundary, right. So, I can have electric fields and magnetic fields on either side pervading, but we would like to know what is the condition that they have to meet at the boundary, right. And we cannot use the point form of the Maxwell's equations at the boundary, because the gradients or divergences and curls are not defined at the boundary, right, because the parameters epsilon 1 and epsilon 2 could be different. Similarly, mu 1, mu 2 could be different, and sigma 1, sigma 2 can be different, right. So, in principle, since there is a change in the media, we can expect the behavior of electric and magnetic fields to be different on either side, but we will need conditions, right. In order to solve for such situations, we will need certain boundary conditions to say what the electric and magnetic fields have to obey, right, at the boundary, sort of like a handshaking, right. Okay. So, we resort to the integral form for Maxwell's equations, so let us start with the electric field. Let us say that I have some electric field. Remember that I have drawn this as a two-dimensional figure, right. So, remember that this is truly a 3D problem, okay. The electric field vector could be oriented in any orientation, right. So, this green vector, you kind of have to assume that this is an arbitrarily oriented electric field vector on the left hand side. But nevertheless, this electric field can always be broken into two components. One which is perpendicular to the interface, right. So, now the reference for us is the interface, and I can tell whether the vector is perpendicular to the interface or along the interface, okay. These are the two directions I can decompose the vector into, right. So, we will call these the tangential components E t, and the normal components En. Okay, remember that E could be varying as a function of time and space, right? But at the interface in region 1, right, it will have to obey certain properties as dictated by the material parameters, right? But nonetheless, regardless of the direction or orientation of E, I can always get a component that is along the interface plane or perpendicular to the plane of the interface. Okay, we call them Et and En. So let's consider a loop . Okay, so we are considering a closed contour where let us say that this width is W and this width is L. Okay, and I am going to apply the Faraday's law, right. So in the point form we had this as curl of E is minus dou B by dou T, right. But in the integral form, I hope you can recall that this is the same as the closed loop integral of E dot ds, right. So this blue contour that we have, that is a closed loop, and it also encompasses a rectangular surface, right. So this is equal to minus of the surface integral dou B by dou T dot dA. So whatever flux, magnetic flux that is flowing through this contour, if it is changing as a function of time, then we have a finite closed loop integral E dot ds, right. This is what it told. So we are going to write out E dot ds for this loop, right. And what I am going to do is align this loop, right, along the tangential component direction, right. So remember that E tangential can be in a plane that is parallel to the interface plane. So I am just going to draw out the contour such that the E tangential is along the side that is shown with side length L, right. So in that case the integral becomes a bit easier. We can say that Et1 times L plus En1, the normal component in medium 1, right. So remember that this is sort of symmetric. So I can consider this width as W by 2 and this W by 2 for a total width of W. So En1 times W by 2 plus En2 W by 2, right. Now if you assume that the electric field vector orientation, right, so we always say upwards is positive electric field, right. If that is the convention, the trip down in region 2 is in the opposite direction. So we will have minus Et2 L minus En 2 W by 2 minus En 1 W by 2. Right. So, this is the line integral around the contour. So, we can actually also allow for the fact that the electric field, the En component, is actually different at the top and the bottom, right. So, if we were to give these right. So, the normal components measured at A, B and normal components measured at C, D could be slightly different, right, because of the spatial separation by L. Okay. And this on the right hand side is going to equate itself to minus of dou B perpendicular by dou T times LW. Right, B perpendicular is the magnetic field that is perpendicular to the plane of the screen, right, that I am writing on. So, perpendicular to A, B, C, D, whatever is the component of the B field along that, we are just interested in the time derivative of that component, right, and that multiplied over the area L times W. Now, we are going to set W very close to 0 in the limit W tends to 0. Okay. Why are we doing this? Because we are quite interested just at the boundary, right. So, we are going to look at what the fields on just either side of the boundary, what they have to be, right, what condition that they have to obey. So, in the limit as W tends to 0, some of these terms vanish, right. So, this terms with W, they all vanish, right, and remember even the area becomes vanishingly small, right. So, the right hand side also becomes small, right, because L times W, where W is shrinking very rapidly to 0, is encompassing a vanishingly small area, right. So, the magnetic flux through such a small area is going to be negligible. So, in this limit we notice that ET1 minus ET2 is equal to 0. Okay, the L's cancel off, right, and we find out that the tangential component of the electric field has to be equal going across the boundary. Okay. So, we will call this the first of the boundary conditions. Okay. We can also generalize this into a vectorial form by saying n cross E1 minus n cap cross E2 is equal to 0. Okay. Now, I have to define what n is. This is the convention that we are going to use for all the boundary conditions. N is a unit vector, right, its magnitude is 1 and the direction is perpendicular to the interface, and the direction in which it is pointing is from region 2 to region 1. Okay. So, please look at it, the tail is in region 2 and the head is pointing into region 1. Okay. This is our convention. This is an arbitrary convention, but we have to be consistent, right. So, we have just picked this and we are going to keep this as the convention for all the 4 boundary conditions, right. So, I keep saying 4 boundary conditions, right. I think that should be synonymous with the number of Maxwell's equations we have, right. So, for each Maxwell's equations we are going to get a certain boundary condition. Okay. So, the Faraday's law in the integral form has given us a boundary condition that dictates that regardless of what your epsilon, mu and sigma values are on either side of the interface, the tangential component of the electric field has to be continuous, right.